Yeah, welcome everybody. First, I would like to give you a brief explanation of what we are trying to do here. So obviously we are doing a video recording, so you could watch this. What is the purpose of this? This purpose of this came when I was having a few meetings or few discussions with some of my close friends. And we realized many of today's students in the high school and college level, they find mathematics as a difficult subject. So the statement is that mathematics is difficult. Now, obviously, it begs a question. A few questions, really speaking. What is mathematics? I think is the first question we'll need to answer, because that is not one subject. What is it? Then, why is it difficult? And why is that a problem if it is difficult? And how do we repair this? So there are a few questions there that we wanted to answer. As a person, I never really found mathematics as a difficult subject. Actually, I found it very interesting subject. Probably because I had some inspirations from some of the excellent teachers in mathematics that I had. I will recall as a tribute before we start this discussion to my teacher, dear HRS, who taught me basics of calculus and algebra about 54 years back or something like that. So he definitely inspired me. See, what we need is, most of us, we have a brain, all of us, as you know, the medical research has shown, even chimpanzees have a brain span which is about 98% same as human beings, or 95% or whatever. So that means two human beings definitely will have a brain span or capability of the brain which is equal to each other by at least 99.9% or something. They're equal anyway. So that means I am as brilliant as Isaac Newton or Albert Einstein. But only thing is there is a big difference what they did and what I did, what I am trying to do. So definitely there is a difference in the way we make use of that brain. So the main problem is not the question of the brain. Everybody has a brain. The only catch is how do we make use of it, We don't use, in fact, as a matter of fact, no humans use more than 20% of their capacity, or even 10%, I think. 10% is what we use. All you need to do is use one additional 0.2%, and then why maths? Give me any subject, anatomy, physiology, chemistry, botany, any subject you give me, I'll be brilliant in those subjects. All I need is to use what I already have in my brain, 0.2% of that, And how does that happen? The question is, it's not like mixing coffee saying I'll add another spoon of sugar, you can't do that with the brain. How do we do with the brain? Because brain is a self-generating program. That means it programs itself. It writes a program for itself by itself. There is no programmer there. So we have to make our brain write a program such that mathematics becomes easier. So that is the question that we have to address. Now, on that aspect, what I found is I can only think of, there is no solution for this, there is no answer for this question. How do you make brain think the way you want it to think? There is no answer. Nobody has given an answer. What we can do, or what I can do, is share my experience about how I got maths to be an easy subject. What inspired me? I'll give one very simple example. We say Isaac Newton was a great, obviously, a great mathematician, physicist, astronomer, put all those words together, one of the greatest, correct? But he was inspired by something called decimal fractions, which Babylonians discovered 3,000, 4,000 years ago. Something which inspired him. Apparently, that means it taught me only one lesson, that what inspires one person. In Europe, I'm sure around the time of Newton, there were literally thousands of astronomers, physicists, mathematicians, all those people were there. And this decimal fractions, whatever it means, I'll explain that later on. I may want to, you may want to hear that answer, but that's immaterial, that's not important. Out of those thousands of people, apparently only Newton got affected by that, by that particular. That means you will never know. Like we say in Kannada, we don't know which hole has got which snake. So that statement in Kannada, I have just literally translated that. You translate it to your language, then you will understand what I am saying. So we never know. We never know what aspect or what story or what experience inspires different people. So what you will have to do then in that case is, let us hope, we'll go through so many hundreds of different experiences. Hopefully one of them will inspire me, inspire my brain, so that I learn mathematics fantastically. I used to score 45% in my maths tests and exams. After this, I got the inspiration. I started scoring 85, 90, 95. Okay. So that means there must have been something there, in Shimoga at that time, which suddenly MLS Shastry, he was nowhere and he is there, I mean, I'm not anywhere. I'm not there. I'm not like these people whom I have listed. These people I have listed are some of the most brilliant human beings I can ever think of. Unfortunately, our history doesn't go back in time. Recorded history, it stops at 500 BC. So before that, there's not much of names of people who invented things and who discovered things and so on. I've written one generic name, Babylonians. What is Babylonians? It's not one community or one set. It's not like Indians or not like Greeks or Romans. There is an area, perhaps I could show you the detailed globe, but I can't really show it. It's actually a small patch of area in Iraq. Iraq, Iran combined, because in those days it was called Persia. So basically a Persian empire which covered Iraq, Iran on part, and top of Africa, which is Egypt, part of that Egypt just covered, and Turkey comes in between, part of Turkey, which is Anatolia, up to Greece. So this is a small patch. This is the patch. In fact, that patch of land, we should really include one more part to it, via Pakistan to Sindh river, Sapta Sindhu river. We call it Sindhu river. Sindhu river is not here. It is in Pakistan today, but then that is Indian. So it's a Hindu river. In fact, our name Hindu comes from Sindhu. Remove the S, it becomes Hindu, right? So that Sindhu river banks had a great civilization. What you might have read the history as the Indus Valley civilization. Indus, they called it Indus. That's a westernized name for Sindhu. And that they had a trade relationship with this, you can call them Babylonians, you can call them Mesopotamians. You ever read about Mesopotamia culture? There are Akkadians, Achemenidians, there's so many different cultures there. But generally the Persian Empire. So that's the region which is known as the Fertile Crescent. That is where about 5,000, maybe 10,000 years ago, agriculture was developed after the Iron Age, and people started looking slightly more civilized. Okay, so that's the beginning of that. So now what I've already started talking of the history. I should go back to my original talk of why mathematics is difficult. First, what is mathematics? I only told you about how that is difficult and how possibly you can address that issue by exposing yourself to different experiences, so that hopefully one of those would trigger something in the brain, so that you start becoming good in mathematics. You are very bad till yesterday, and now today onwards you are very good. So that is the objective of these 12 sessions that I am sharing with you. Now, first is, what is this mathematics? Mathematics, earlier there was no science, didn't exist. Mathematics didn't exist. With these old civilizations that I mentioned about, there's a bit of arithmetic which is going on, because for trade and maritime trade and day-to-day exchange, just saying, last year I gave you 3 cows, this year you have to give me 4 cows, some counting, a small counting. So that is the arithmetic part of mathematics. This is the first area which got developed, correct? And most of the initial work of arithmetic was developed by Babylonians, actually. And I think in India also, parallel developments might have taken place, or they might have exchanged those ideas in that route, I showed you from Iraq to India on the map, correct? So arithmetic got developed. Then day to day also there is something that we always, even today in the scientific world, we should not believe something in pseudosciences, and we should not believe, but unfortunately it is human nature. We believe in what are called omens. Omen. So we can have a good omen or a bad omen. I mean, these omens are generated because of repetition. So, like for example, I am going to work every day, let us assume. May not be an office, could be the agricultural field where I am doing agriculture. So for the past few months I have observed, that every day when I go, I have seen one cat, white cat, crossing my path from right to left. All those days my work was very happy and I did fantastic work. But on some days, occasional days, I have seen, like last Wednesday and Friday, when I went to the work, the same white cat crossed my direction from left to right, And that day I sprained my foot and I had a problem, and then you come to believe, tomorrow when you are going to work, suddenly now you are saying, where is the cat? Where is the cat? Is it going to go from the right to left or left to right? So if it goes from left to right, God help me, I don't want to go to work today. We go back home. You understand? So this believing an unrelated event to the future, that is an omen. And sometimes it can be a good omen also. So you can have good omens and bad omens. So people are always looking for these omens. Now these are all on the terrestrial. On earth these omens are man created. You can always shoo the cat away or something, so it doesn't cross the path. So, whereas there are some omens which you can't control, and therefore you can believe them more ruggedly. These are the cosmic omens. So we have terrestrial, that is, terrestrial is on the ground. And we have the cosmic. Cosmic is cosmos, is the sky. I have no control over where moon comes or where moon goes or when sun sets, where sun rises. We have absolutely no control. And if I can think of a cosmic omen, so that means omen is always some kind of a special, unique event, which occurs. So that is an omen, right? So what are those omens in cosmos? You could think of eclipses as one important. Eclipse obviously is a cosmic event where suddenly for some time you don't get to see moon at all, or you don't get to see part of the sun and so on. And that might apply to other planets like Mars and Venus also. So you might have eclipses. Then you have this so-called conjunctions. Conjunction is almost like an eclipse, except that we are talking of not the sun which is involved, but two planets and the earth, they come to the same line. So that means as seen from the earth, you will see one planet going across the other planet. So on the same line of sight, basically. That's a planet conjunction. That could be an event. Or an arrival of a comet itself can be a conjunction, right? So, a special event. So these are all cosmic events. Obviously, people were looking for these cosmic events to tell us something which happens on the ground, and they relate it That basically that means we are getting into a new area of mathematics. You can think of that as astrology and astronomy. So they are obviously related. Both are astro. Astronomy is study of the skies. Astrology is predicting what can happen or whatever. And in these aspects, we normally have some royals or some big fellows of the time. They would be interested in astrology, definitely. And obviously they would, or even at a later time, they would like to assign a cosmic event to a great person. Like for example, when Jesus Christ was born, they might have said that something took place in the sky, no? So it's possible, no? So whether it actually happened or not, nobody knows, because at that time nobody recorded that particular history. Same way when Mahabharata war took place, that was the end of Dwapar Yuga and beginning of Kali Yuga. At that time, within a period of 1 month, there were 3 eclipses. Normally you would have about on average 1 eclipse every month, moon or sun or whatever, or less. But that one particular month, there were 3 eclipses which took place. So obviously it signifies something, and that's why I said, boss, I think our Dwapar Yuga is over. We'll go now, we'll call it Kali Yuga. Something has happened in the sky, and obviously something is going to happen on the ground. Things are not going to be the same. So that is so that becomes astrology has become astronomy. So that is the next subject. Then if you want to study astronomy, what happens is that you need to do some measurement on the sky. You can't measure anything on the sky. You can only measure some angle of view. Where I can see the sun at what angle, that is, or moon or planet or whatever, that I can see. So obviously the next was, since I can't measure in the sky, we'll measure on the ground. So that is the subject which took birth next as branch of mathematics is geometry. Geo refers to earth in Greek language. Geo or G, earth. And helio is the sun in Greek. Obviously you will find, since it originated there in Greece, you will find many words from the Greek language as part of this nomenclature. Later on, Romans did a lot of further deployment of these techniques and so on. So you will find a lot of Italian words or Latin words. So that 2 languages that you are likely to see, whose words have percolated into every sphere of mathematics, biology, anatomy, physiology. Wherever you see, you will find Latin words. So that is fine, all right. So geometry is measuring the earth. So that was the subject which came next as part of this. Then once geometry was there, this gave rise to a special field, a subfield, which became so important that it came to be known by a new name, which is trigonometry. It is a measurement of triangles, actually. Itself, triangle is one shape, of course. Out of so many shapes which are studied in geometry, we have squares, pentagons, octagons, heptagons, circles, and so on. Out of them, triangle is one shape, 3-sided figure. And the study of the triangle became so special and so advanced that it has become a totally new subject by itself, trigonometry. Then somewhere at the back of this, arithmetic was not really systematic, and to make it systematic, a new subject got developed, which is algebra, which is the theory of equations. It got evolved. History, I'll show you when it came into fruition, when it started. Then eventually, when these planetary motions were properly studied in the 17th century by Tycho Brahe, Johannes Kepler, and Isaac Newton, and those astronomers, they needed a new branch of mathematics because the existing geometry, algebra, and astronomy will not do that work. So they invented a new subject, which is the calculus. I basically listed only some 6-7 branches of mathematics, but each of these branches has spread into many sub-branches, and you will find many more subjects and the combinations of these subjects also. You will find some part of geometry done using algebra called analytical geometry, and part of the calculus has come back into theory of equations, into algebra. So there are so many different arrows of evolution and development. Is one of the reasons why mathematics has become confusing subject, because it is like a huge forest of so many trees. Each tree has got so many branches, one branch leading to another branch, leading to another branch. Each node, you can think of that as some kind of a theorem or something. So one theorem leads to another, which leads to a corollary, which to a third theorem, and so on, right? So each subject has got so many thousands and thousands of such statements and observations. And in addition to that, from one subject to another subject also, there are one branch of one tree is connected to one branch of another tree, and so on. So there are some interconnections also. So that leads to more confusion. So one of the reasons why mathematics has been confusing was that. So what I thought was to break it down, we look at the elementary stages of mathematics evolution. Like I said, when only arithmetic was there, everybody was happy. I don't think it was difficult, right? So all we need to do is add a little bit of maybe astronomy and geometry and algebra and trigonometry and calculus, and we know mathematics now. So, I mean, when you add it, is how do you add these is the need of the moment. No? So all these things, in fact, the entire science revolution has taken place because necessity is the mother of invention, right? In fact, calculus was invented by Newton because there was a need for it. Otherwise, he wouldn't have wasted his time inventing a new branch of mathematics. Newton was not a mathematician. He was a physicist actually and an astronomer. He had no interest in mathematics, but then he could not do those astronomical calculations with the existing knowledge of algebra and geometry and trigonometry. So he said, I need a new branch. I need a new way of doing the calculations, and that became calculus. So it's always been necessity. So if we go back in the history and see the necessity at various points of time, starting from 2000 BC, I've gone till 18th century. I think I stopped there, doesn't matter. I'm sure there are many more developments which have taken place in the 19th century and the 20th century, but then the important interconnections between the different branches of mathematics have taken place around this time. No? This is the end of that period. So I would say 18th century end is our timeline. Starting from 2000 BC, that's about, it's not a small period, it's about 3,700 years of evolution is what I'm talking of. So we could look at the history of this 3,700 years. Purpose is multiple purpose. Why I want to look at the history? One, of course, obvious reason is I want to pay tribute to at least some of these names there. These are all great scientists of all time, great mathematicians, great astronomers of all time. So we would like to pay tribute to them. That is one. Secondly, we would like to find out how some of these people actually discovered some new things in mathematics and how it became a new branch and so on. So we would like to look at those aspects also. Definitely we are interested. So history gives us some excitement in terms of the knowledge, one aspect. Secondly, like I said, I am always looking for that, for the whole, which can inspire you. So I don't know, this could be the whole for you. So for some of you, for one of you, if it is the whole, that should be sufficient, right? So that is the second reason why we are doing that. So the two reasons I am going to do that. And third, it gives me time to talk about some issues which I always wanted to tell you people. So I would like to tell you that. So why don't we just have a look at the history of scientific revolution? Okay, do that. Now, when you are looking at the history, like I said, I have listed Babylonians as a generic term. which includes probably thousands and thousands of mathematicians at that time, geometers as they were called, arithmeticians and geometers. Geometers is a geometry specialist. Now we don't know their names. So what we do is we select one name and pay tribute to all of those people. So that name would be Pythagoras. Pythagoras is Pythagoreans, what I have written, 300 BC. Pythagoras is from Greece, of course, and we named a theorem after Pythagoras called Pythagoras theorem. No? Simple theorem. I'm almost 100% certain that Pythagoras did not discover that theorem. It was discovered by Babylonians much, thousands of years earlier, and probably even by Indians, Sindhis. Doesn't matter. We call it Pythagoras theorem, and that is my way of tribute to those people that we are talking about, Babylonians. What did they, like I said, they developed this arithmetic. The purpose was to do some day-to-day simple computations. See, they could do multiplication, they could do addition, subtraction, but they did not have a division. Don't ask me why. That is the kind of... and they used a base, actually, positional base, and the base was 60, not 10 or 2. 2 is binary, 10 is decimal, and they use the base 60, which is known as sexagecimal. So they did all their arithmetic in decimal arithmetic. So 60, the reason they use 60, because they did not have division, because 60 is a nice multiple of 2, 3, 4, 5, 6, 10, 12, 15 and 20 and 30. You know, it is divisible by all of these numbers and very easy to write fractions of using 60 as the base. It makes life simpler. So I think that's the reason they use 60 as that base. So 60 is almost has become a sacred number, you know, in those days. Anytime you want a number, what is the next number that you want? Let us say we have 1 hour duration and we want to split that as so many minutes. Tell me how many minutes we should have? Obviously 60 minutes, because that is the number, no? It's a magic number, so 60 minutes. And similarly, 1 minute divided into 60 seconds and so on. So that's the origin of that 60, you know. Remember that 60 is that base of Babylonian arithmetic, which became popular. And one more thing these Babylonians did. We have one day, we have said it is 24 hours, correct? No? Is one observation that we make. Next, we have this angle, what you might call the full angle. No? Full angle is one complete, starting from one direction, east, the full angle, complete and come back to east again. So what is that measurement? Is 360 degrees, what we call 360 degrees, right? So I would like to give you a justification for these two. Next, it gives you an idea about the history of development. At the same time, it gives you the actual reason why we use 360 degrees. And half of that is 180 degrees and 90 degrees, right angle and so on. So we are using those numbers. And we should not use a number just like that without knowledge. So that is one aspect. And gives us good look at the history also. Now, I have explained why 60 minutes and 60 seconds were used, because that was the base of the arithmetic of Babylonians. And obviously, at this time, 500 BC or so, I have written one name here, Thale. Panini is Indian, of course. Thale is known as the father of geometry. We would like to pay tribute for each subject, would like to pay tribute saying who is the father of what. You know, so that we get an idea of how we did the development. Thale was one of the earliest Greek persons who was interested in development of geometry. And obviously, first thing our friend did was to, they already Greece and this Persian kingdom region, they're always at war with each other, and they're nearby, maritime distance is quite close by. I think he went there, or he already had some people from there, so he studied Babylonian mathematics and then brought the whole thing as part of the base knowledge and developed it. So we call him the father of mathematics, which means father of geometry. Geometry was the only subject, so he is also the father of mathematics, if you want to call him. And there was no other science subjects in 500 BC, so obviously he is also father of science. I mean, if you want to give a name, not Pythagoras, but it is Thale. That is fine. Now, coming back to what he brought from Babylonians, part of geometry, yes, and this, because of this sexagecimal system, the 60 became an important number in most of their arithmetic. Then next is the astronomy itself, the astronomical observations which Babylonians had done. Now, I'm telling you that that is a very difficult subject, because, of course, today because of pollution, we don't get to see the sky, clear sky. Even without pollution, if you look at the sky, when you say, I want to look at the sky, what are you seeing? No? Sky is actually, Earth is somewhere in the space, is all around. No? 360, I mean, it's not 360 degrees, it's a volume. No? It's a huge volume. So if you look at Earth as a globe, Earth is not perfectly spherical, but approximately it is slightly compressed on the pole side. So you got the two poles here. And the equator, right? It's not the equator. Equator is here, okay, whatever it is. So now you see, if you say, I'm standing on the Earth, that's where we are standing now, what you get to see is the vision at the lower side, it ends here. So you will see only half of the space. You can see half of the space from the plane, on this plane. You draw a plane from this, half of that above only you can see. Of course, night time, you get to see the other half, which is below. No? So we get it within 24 hours, we see the entire space actually. And observing the space, how do you do astronomy? You know? How do you do calculations? Because you can only see angles on this. You can't walk there and measure. There is no question of measurement. No? How do people did that? How did Babylonians did that? Was a question I've been asking myself for the past 1 week, studying a lot of documents. It's not simple, because the reason that we know right now the view of the sky changes because of at least 5 or 6 different reasons. No? What we have as a picture of the universe, if you think of the universe as we talk about it today, so that is the real picture, what is there as universe. But then at the Babylonians' times, obviously this universe was not there. What they see and what they recorded only was the universe, right? As far as Greeks also concerned. So what is the universe? Sun is one of the stars in the Milky Way galaxy. Each galaxy contains billions of stars, and there are millions of galaxies in the universe. So you can imagine the size of the universe, so huge. And the sun is not even the biggest star. It's a medium-sized star, whatever class they write. There are stars which are 4 times or 10 times or 100 times or even 1,000 times bigger than sun. But unfortunately, they are so far away, the distance so far away, we see it as a tiny dot in the sky, right? But there are billions. Actually, number of stars is billions and billions. Beyond what we see also, some are not even visible to our naked eye, right? Till about 1545, we have our friend Galileo, who invented the telescope. Telescope became part of scientific instrument only in 1545. No? So before this, all this time, people only looking at sky with naked eye, correct? No? So naked eye, what you can see? Sun is one such star, and it has got 8 planets. Actually, used to be 9 planets, but I think scientists have disqualified Pluto as a planet. No, they removed it from the list. Doesn't matter. Now, the closest is what we call Mercury. Then we have Venus. Mercury is quite small. Then Earth is where we are standing right now. Then Mars. Then you have Jupiter. Let me write the names, I think. So we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. These are the 8 planets which are there right now, and all of these are going around the moon, going around the sun. Moon is one of the satellites of the Earth, which is, you should really show it next to the Earth, is going around the Earth at the moon, right? It's quite small, probably is as big as, or maybe slightly smaller than Mercury. So all these planets, Earth along with the moon, no? And by that token, Jupiter, I should really write at least 4 moons which are going around Jupiter. That is the big moons. Actually, there are 8 big moons and then about 270 small moons. So Jupiter itself is like a mini solar system. They call it the Jovian system. Jovian. That's the real fact, what we scientists have observed today. Anyway, so this each of them is going around the sun in an elliptic orbit. That is the first movement that you see. And if you take Earth, our focus is on Earth. So let us just look at Earth. Because all our view is a naked eye view from the Earth. What Babylonians or Greece astronomers used to see. So Earth is flattened at the 2 points, what we call the North Pole and the South Pole, correct? And if we join these, we get an axis, and Earth is spinning on that axis. So there is a spin. The spin is once every day. Why does the Earth know exactly how to spin exactly once per day? How does it do it? You might ask that question, right? Why not take 1.5 days or 2 days or 1.1 day? Why does it do it exactly once every day? Or another question, this Earth goes around the sun one full round of revolution around. This is revolution. This is the spin, right? This movement is once every year. Exactly every year it goes once around the sun. How is that possible? You might ask. Actually, answer is very simple. Measurement of time. So measurement of time has been a very important aspect of science. It has taken a lot of effort of thousands of scientists to perfect the measurement of time. So our units of time starts with these figures. One, of course, is the sun-based, or what we call solar. Solar is an year. So one moment of Earth around the sun, we designate it as 1 year. Then one spin around itself, we designate it as 1 day, right? That is the time Earth takes to go around. Yeah. Now, the question I asked, the reason we came here was because why the day was split into 24 hours. So, whereas hours are split into 60 and 60, day also could have been split into 60. 60 hours was more natural in the Babylonian time, but why did they make it 24? Reason is very simple. Like I said, when you say I am standing on the Earth, right, and looking, just visualize this picture. You are standing where on the Earth? I don't know where, which is some point. And we look at that. We are looking at, if you draw a plane which is tangential to the Earth globe, you are seeing this part, half the sky, or half the heavens, or half the cosmos, or what we call the celestial sphere. Celestial sphere is the complete 360-degree view all around. All around the earth is known as celestial sphere. So we are looking at half of that and half of that during the night when the earth goes around, right? So, and earth also, let me just finish this movements first and then I'll come back to this topic of the view that we see. So now earth is spinning once every day on this north-south axis. Unfortunately, this axis is not parallel to the path around the sun. There is a slight inclination. So that means it is going like that. I don't know if you can visualize that. I can show you in this. No? So now assume this is the north-south axis where earth is turning, right? I did that. Very nice. It is turning like this, right? Now, this movement, if it is going around the sun, I'll walk like this. No? This is not exactly in line with that. It is slightly inclined. About 24 degrees or something. It is turning like this, but going like that. You understand? This turn doesn't change. It's like a top. The spinning of earth is like a movement of a top. No? So, when you say I've got a top, we play the top with a string on the ground, you will find it is spinning very fast, right? Vertically, it's standing vertically. And when you push it a little bit, just apply one little pressure from one side, you know. Just push it like this, it doesn't fall down. What it does is, it starts, when it's turning like this, it starts gyrating, you know, what you call gyration. So this is a point. A point on the ground remains the same. It is turning also, spinning. At the same time, it is going around a small circle like this. That movement is called precession. So earth is actually doing precessing also. That means that the angle of inclination that you see is not fixed. That is going once around like this, no? As it goes. So for some time it is like this, always inclined like this, in this direction. But after some time it will be like this, the opposite direction. Always going out like that. You understand? And what is that duration of this? Same way like we wrote 1 year it takes to go one round. For this axis precession, for one precession round, how much time does the earth take? Let me give you an approximate figure. Is about 26,000 years. So it's a huge amount of, it's a very slow change of direction. It takes 26,000 years to go one full round of precession. Okay. Now that means that, see, this angle itself is the cause for most of the seasons that we see, you know, on earth. Like we have spring, autumn, winter, and so on, right? Those are because of that angle only. So obviously that is going to change. What was winter once actually will become summer, no? But then not tomorrow, it will happen after 26,000 years anyway, which you and me won't see it. Okay? Doesn't matter. That is one aspect. So that is you got a spin, you got a precession, and you got a movement around the sun. So I have listed 3 movements of the sun already, of the earth already. Then there is a 4th movement. The sun, along with all the family, you know, the full, what we call the solar system of all the planets and their moons and so on, is actually doing a movement around the center of the Milky Way. So it is going one round. You know. That is it's quite fast in terms of miles per second, but then in astronomical distances it is not much, no? But it is moving. That is one movement. The entire solar system is rotating around, is towards the edge of the Milky Way, so it is going around. Maybe after another 1 or 2 billion years, it will be on the other side of Milky Way. That's the time. Then one last movement, that's the 4th movement, and there's a 5th movement also. The entire Milky Way itself, with all its billions of stars, is moving away from other galaxies at lightning speeds. What is the lightning speed? You can imagine. No? It's moving away from other stars. But the distances are lightning large when compared to lightning speeds, so it is not very apparent. No? So we are talking of astronomical figures, what we call astronomical figures of these. So obviously, I'll give one simple example of an astronomical figure. what is the distance from sun to earth or whatever. No? Simple, one simple distance we measure in kilometers and so on, right, is about 200 million kilometers. So you can imagine, the distances which are involved. And Earth is only here. But beyond Earth, once you go beyond Earth and Mars, these are what are called inner planets. No? Mercury, Venus, Earth, Mars are inner planets. Then you get the outer planets. Jupiter will be somewhere here. Saturn will be on the next building. You know, you see that distances also increase. Saturn is about, I think, something like 4,500 million kilometers or something. So when compared to 200 million kilometers. So obviously that is so far away. Pluto is even further. That's why they dropped it, saying it must be something. You know? So leave it there. So these distances, in those kind of distances, obviously what happens is one peculiar thing happens. Let me just explain that because that is required to understand the view. Now I'll rub this picture because this is not the picture which our friends knew 3,000 years ago, right? 2,000 years ago. So this is the picture which we know today, all these 5 movements. Earlier time, what Greeks thought or what these Persian people, Akkadians thought was that Earth is a solid place. Earth does not move. In fact, for quite some time, Greek astronomers refused to believe that Earth can be spinning on its axis, because they said if Earth is spinning once per day is what we are talking of. Just imagine, what is the circumference of Earth? I don't know if people know it. Is about 25,000 miles. So that means on the surface, you can see if Earth is spinning once every day, surface, the movement, the speed of the ground is about 1,000 miles per hour. It's correct. And if it is moving, the Earth is moving, remember the air is not attached to Earth. No? Whatever is attached to Earth, like a mountain or this building, will move at 1,000 miles per hour, no problem. But the air is not attached, it is free, right? So obviously we'll get a breeze in the opposite direction, no? Reaction. We'll get a breeze. They said it's impossible to visualize a 1,000 miles per hour breeze coming at you from east to west, because this is supposed to go from west to east, right? Earth is turning from west to east. That is, I don't think it is possible. So they never believed it. They said it's impossible. Earth is a rock solid place. Yeah, come on. How can you say this is moving? You can see now, it doesn't move. Earth does not move. So first they assumed that. And because of that, now you see all these 5 movements, what do they do to the picture that we see standing on the Earth? I am moving, but I don't know that I am moving. No? So, like one simple example, supposing you are traveling on a train. Straight line. We are traveling on a straight line on a train. You are sitting inside the train, correct? You are sitting inside the train and you are looking out through the window. And train is moving at some decent speeds, maybe 50 kilometers per hour or whatever. Correct? So in 1 hour it travels 50 kilometers. Correct? Now if you see outside and see some distant object, you can look at several objects, you can look at some object which is close by, maybe there is a tree or something like that. And there may be a building here. And at very far away, probably I can find a mountain or something, right? No? I mean, this is not here. Assume this mountain is very far away. So when you look at that, we are looking at it with one direction, right? Now, after 1 hour, we have traveled 1 kilometer, and look at the mountain again, right? So we are moving like this 1 kilometer, look at the mountain again. Actually, so what is the difference? Obviously, we will see at a different angle. No? So what is that angle? That angle, if you draw this straight line earlier, what we looked at, and after 1 hour, what we are looking at. This angle is known as a parallax. Parallax angle. But then I have shown the mountain here, so you can see the considerable parallax angle. In the real case of when the mountain is about 10 kilometers away, you will find that angle. You just visualize the 2 straight lines that you draw from here will be so small, It's practically you can't make out. So that means mountain looks like it is standing still, doesn't look like it is moving at all. It is a parallax which is mistakenly telling you that they are moving. No? This mountain doesn't move, whereas you take a nearby object, you can see it is going in the opposite direction of our movement very fast. Nearer the object, the faster it looks. The closest electrical poles will go back. I mean, they look like they are going back at 50 kilometers per hour. Slightly you go further, they are moving at 30 kilometers per hour and so on. Eventually, when you go to a distant mountain, they are not moving at all. No? Because I can't make out. No? So you understand? Once the distance increases, this parallax error keeps getting lesser and lesser and lesser, right? So which means, now coming back to the Earth view of the sky, cosmos, viewed from Earth. I told you these galaxies and stars are so far away. We have a nearest star which is about 4 light years is the distance. Light years is the distance light travels in 1 year. 1 year consists of 365 days, which consists of 24 hours, which consists of 60 minutes, which consists of 60 seconds. You multiply all of these, you get on a big number, no? That is the number of miles plus 4, multiply by 4. That's the distance to the nearest star. So, and there are some stars which are 100 light years away. There are stars which are million light years away and billion light years away and so on. So people are seeing today through their telescope and advanced instruments. So obviously at such great distances, the parallax is practically zero, right? So that means they don't move. Stars don't move is the question because of Earth movement around the sun. See, we are talking of the Earth's movement around the sun. But then, because we are standing in the Earth and Earth itself is spinning on the axis, north-south axis, the stars look like it is moving in the opposite direction. So the entire upper celestial sphere will look like it is going back in the opposite direction of the Earth's spin. That is the view. Correct? So we'll develop on that, how it affects our view next. Yeah, now like I was telling, these stars, what you might call distant stars, and there that parallax is so small, it is zero. Why forget about naked eye? Even with a telescope, most powerful telescope of Galileo or today modern telescope, you cannot even measure that angle. It is so small, close to zero. So we can practically assume the stars are fixed. Distant stars are fixed in the sky. Okay. But then, of course, the revolution of Earth is there. Spinning of the Earth, because of that, the entire cosmos is turning from west to east. That is there. And that's what the Greeks also believed. And Babylonians also believed that they couldn't think of Earth revolving. No? So, spinning on its own axis. So, obviously, they believed that the entire cosmos is a big celestial sphere. There is a name, celestial sphere. And that sphere is turning around once per day, every day. Why it is doing that? Why is a question we won't bother answering, right? But then, what happens to our view is the question, right? So, assume that naked eye view of a person standing somewhere on Earth, You take the map, you can actually put him right on top of Babylon if you want. Babylon is an area somewhat south Iraq or something like that. So assume the person is standing here. Obviously, I have not drawn the person to scale. No. Earth, the size of Earth, right? So anyway, what he can see is you draw a plane which is tangential to the Earth's surface, and we have the celestial sphere, huge sphere, with astronomical distances, unimaginable distances. And he is seeing half of it actually. That's what he is seeing, half of it. And there at that distance, if you just turn your eyes like this and see, what you can make out, you'll see millions of stars actually. That's all we are seeing. But then we see star clusters. cluster means don't think they are close by. One may be very far, another may be not so far. I mean, not so far itself is thousands of light years anyway. I'm saying, it could be there. But then human eye cannot make out that depth, So obviously they look close to one another. So, and some stars are brighter, some are not brighter. One star is brighter probably because it is nearer, or probably because it is really brighter. Luminosity is more. There is more energy which is being produced. It is 100 times the sun size. Obviously, it is more luminous, or because of the distance. Either way. So when you see those stars and the star clusters, what does that remind you of? You just look at the sky like this. What I am seeing is only 180 degrees, of course. At any given night, one night, if I stand at a high point so that there are no obstructions, I can see, literally see, I can see 180 degree of that sky, right? And the area, the sky also is huge either way, in either direction. But my interest, remember, is not in stars. My interest is in the planets, what we think as planets. So what are the planets that these Babylonians saw? Is the first question that you have to answer. So what is the first planet that they saw? Is the sun, the biggest planet. I mean, planet is the name that we give, but sun, any cosmic object is a planet because that is going around the earth. Everything is going around the earth, so they are all planets. The first biggest planet that you see is the sun. Next biggest that you see is the moon, second, right? And third you see is Mars. Fourth is Mercury. Now Mercury, even though it is closer than probably Mars, is so small. See, depending on the size now we are thinking that some planet is bigger, some planet is smaller. Sorry. Then you have Jupiter, which is one of the biggest planets in the sky, next to Sun and Moon. Then Venus and Saturn. Saturn is not as big as Jupiter. It is probably twice the distance when compared to the distance of the Jupiter. But then it has got those rocks going around. It looks like a ring. It looks very nice actually. If you see photos of all these planets, you'll see everything except the sun. Everything looks the same. Moon also looks like a bare sphere. Mars also looks like a bare sphere. Everything looks like a bare sphere. Whereas Saturn looks beautiful because of that rings. Saturn ring is there. Ring is actually a set of rocks which are like satellites around the planet. So Saturn looks beautiful. So that's why that. So we have these 7 planets in the sky that I can see. And my interest is only in these planets. My interest is not in stars. We are not interested in the stars, right? So when you say I've got these 7 planets, and we all know whether sun is going around the earth or earth is going around the sun, relatively it is the same. So I also told you that the elliptic paths of all these planets are approximately in the same plane. So that means approximate, not exactly, not 100% same plane, but maybe the path of the Mars is slightly inclined, 1 degree inclination. If you look at the path of the sun around path of the earth around the sun is one plane. That is the orbital plane. There is an orbital plane of Mars also, which may be slightly 1 degree away. Orbital plane of Jupiter may be 5 degrees the other side. So within, I think, a period of about 5 or 6 degrees as an angle measurement, you will find all these 7 planets. You will find in that band. So now that means when I am standing here, I am looking at only one direction. See, I have got all these directions to see. I am looking at only one particular direction because that is the band of that 6 degree or 7 degree where these planets are going around the sun. You see, that is around Earth as far as I am concerned. They are going around. So I am looking at those 7 planets, and then of course they go here. They may be anywhere in this line of sight, or they may be up there, or they may be on the back side also. Obviously, all the 180 degrees I have to see, and some of them may be below also. that I'll see in the morning, daytime. Daytime, probably I can't see because of the sun, but then there is a small period of twilight period where the sky is fully lighted, but the sun is not there, you know. So that is the time, early morning, just before sunrise and just after sunset, half an hour each, may be the best time to see the sky, because you will get good light to see. Some of the planets which are not luminous, Jupiter actually looks luminous, no? So moon looks luminous because of the sun's light. Even the other planets you will be able to see because there is a light there, and sun is not there to obstruct our vision. So my interest in that band only. So that means now you see, suddenly I find moon is there, you know, right there. I can see moon there. Then I lift my head and see moon after a few days, it is here, somewhere up there. Correct. Obviously, moon has started moving there, right? So now I need to find out. Now, how do I find out? We need to measure the angle. From this angle, naked eye, what measurement that I can do, rough measurement. And how do you recognize which direction you are looking at? Remember, we have the reference of the star clusters which are behind the planets. Correct. At a great distance. So you can see that these planets are moving across the star clusters. Correct. And if I can recognize a star cluster, how do you recognize it? Mentally, I visualize something when I look at those bunch of stars. No? Something which looks like a balance. Tula is the name. Correct. I called it Tula. That is a Tula star cluster. Or something which looks like a goat. I will call it Mesha or Aries. You understand? Or something looks like a pot of water. That star cluster. It looks like that pot of water. I will call it Kumbha. Something looks like a fish or something. I will call it Meena. Like, you understand now? So these star clusters, first thing is, we map the shape. Actually, there is no shape, there are no lines there. We only see a few stars around, right? So mentally join some lines and see what does it remind you of on the ground. No? So on the terrestrial ground, it might remind you of something. So we give it that name. So obviously tomorrow when I come and say, hey, look, that is my Tula there. I can see this is my goat. You know? So you understand? I'll be able to recognize the star patterns. And there they. Now with reference to the star pattern, now you see I can discount the rotation of Earth entirely by doing this. The same, whatever Aries, that is Mesha. Now you can see this knowledge of these, what are called zodiacs. These are called zodiac signs. This knowledge originally was with the Babylonians, then it came on to Greece via Thale and Pythagoras and so on. They borrowed that knowledge. Europeans have this, I don't know, good habit, bad habit, whatever. They have a habit of anything they find interesting, they will want to simply take it, man. They won't pay you money also for it. You understand? If they can help it, of course. If they can't help it, they'll pay you money. Say, we'll do trading. I'll pay you money, right? And if you are an innocent, ignorant person, they simply take it and go away, right? So they've taken that knowledge. I don't think they paid Babylonians anything there. Anyway, that is besides the point. We are not interested in history, I'm sure of that. So these zodiac signs, you know, what I was talking of is I can recognize that, and because of this revolution of the Earth, correct? Even these zodiacs are actually moving, no, across the sky, but then I can recognize that. No? So with respect to that, where is the moon? No? You understand? Moon was in Aries some time ago. Now it has come to Meena or something. I can make out that. No? So with respect to these 12 signs, that means by these 12 signs, zodiac signs, very simple. He said, I can look straight like this is one direction that I can identify. Then one up, straight up is one, right? So the two. In between is very difficult to, maybe two more. So that means one every 30 degrees. You understand? That makes it exactly 12 signs. No? Round, full round will be 12 signs. And that you recognize by, of course, these are actually called constellations. Constellations are the star patterns in the sky. Of course, there are millions of constellations all around, but our interest is only the constellations against which our planets are moving. So there we have selected, they selected originally 13, I think, Babylonians, but 13 is an odd number, so they settled on 12, right? So they could map the movement of planets across these 12 constellations, right? And easy to measure, so easy to compare, and I can do the observation anytime during the night. All I need to do is, with respect to these constellations, where is moon, with respect to these constellations, where is Mars, and so on, right? So that makes life simpler. Otherwise, they would have had to observe the sky only at one point during the night, only exactly at one point of time. You see, next observation will be tomorrow night at the same time. No? So obviously it reduces the observation time. Whereas here, I can sit in the whole night, I can sit down and keep watching. Everything is moving, but I can keep watching this. Of course, my direction is limited because I am only interested in these planets, right? So they become so important to me, and they're going to tell us, give us some omens, and with those omens, I am only an astrologer, right? Omens, I'll go back to the chief ruler, royal, no? Chief. I'll go to the chief and say, boss, there is something which happened with these planets today. Most likely tomorrow something else will happen here on the ground. No? You understand? And he'll pay me money for it. No? So for that. So, in fact, sometimes these royals also, they patronized. It's called they were called patrons. The royals were patrons of astrologers. They patronize. The royals themselves don't have time to sit down and watch the sky. You need a brilliant fellow just to do that job. So they would call these brilliant fellows in the village and say, boss, you don't work in the field, do any agriculture for the next 1 year. I'll pay you money. All you need to do is every night you go and check what these planets are doing or what they are not doing. And if some funny business is there. See, they are always looking at an event, cosmic event. They are simply going around without doing anything is not interesting. Something should happen. One planet crossing the other planet, or in the case of Mars, they notice some peculiar behavior of Mars. It is going up for some time, when it stops, then going back a little distance, stops, and again going forward and going around. So this is that means normally all the planets are going around like this. That is the movement of the planets. So Mars had what is called a retrograde movement at some point of time, not always. Occasionally it has got one retrograde movement, which is a stop, go back, again go forward. Stop and go forward. And continue the path as if nothing happened. Of course, you can understand today, we can understand very easily. Just imagine sun is here at this point, and we have Earth. I am the Earth, right? And Mars is somewhat beyond my point. So sun is there. I am going around. Mars also is going. Both of us are going around the sun. No? You understand? Now remember, Mars is farther than the Earth, so it's slower. Obviously, it is slower. So Mars may be there. I am behind Mars now. So now you just look at my vision. I am looking at Mars in this direction, right? This direction. I start moving. Mars is also moving, but I am faster than Mars. So after some time, now you can see, for some time, both of us are approximately parallel. It looks like stopped. Then I go further faster, and Mars looks like it's going backwards. You understand? So retrograde motion of Mars is a simple fact of life. When both have elliptical orbits and they are different point, depending on the point where it is. If Mars is totally on the opposite side, then there is no question of retrograde movement. It is always one single. So occasionally, only when they are together, they come together like this and go, you will find that retrograde movement of Mars. Maybe that's an interesting cosmic event which they can report back and so on. Eclipse definitely is one good thing. So those people, astrologers, started minting money by observing these planets. So obviously, they want to pray to the planet. We want to give tribute to the planets. Correct now? So what do? First thing we can do is, why don't we call each day we will dedicate to one planet. Yeah. I think that's the best way of doing things. Is each day I want to remember one particular planet, tomorrow one more planet, day after tomorrow one more planet. So you say, okay, today, what do we call today? We call it Sunday, because I am dedicating to sun day, right? Moon will be Monday, right? Mars will be Mar day. No, sorry, there is no Mar day. There is I think there is a Greek god, mythical figure, or maybe Babylonian figure, I think Greek, called Zeus or something. There is in mythology, like we have our Rama, Krishna, and Ananta, Govinda. We have millions of names, right, to choose from. They also have millions of names. Greeks also had. Zeus is one of those names. So we'll call it Tuesday. Right? Mercury is Wednesday. Jupiter is strong fellow, no? What we call Guru. Guru is not teacher. Guru is weight, heavy fellow. Thursday. Venus, somehow they associated with a female god or something. I don't know. We call Venus Shukra. That is Friday. And Shani, Saturday is that funny fellow always gives. So now you see, when a person is born, a simple example, the Saturn was in that particular constellation, right? And after 10 years, Saturn is a slow fellow moving around. No? You see, it takes, I don't know, probably the revolution period is some 100 years or something. So after some 20 years, suddenly Saturn has come back to the same constellation which was there when I was born, on the day I was born. So a fellow is saying, you will have one Shani effect on you. Something will happen to you next 1 week, be careful. No? So I'll do one thing. If you want to avoid any misfortunes, I got one special puja that I can do for you. It will only cost you some small amount of money. So why didn't you come? You understand now? That's the basic thing. Then of course, this constellation also is very big, because the angle is only 30 degrees, right? So we wanted to split that. So we split each of them into 4 padas, and say you're born in the first pada, second pada. And what are you? You're born in that Moola or something, so not good, for girls. So why? Don't ask me. You understand? So that now why 7 days are there in the week? Because there are 7 planets. These are the 7 planets. Correct? No? That's the reason. And why we have these 12 months in the year, 12 zodiacs. And why we have 24 hours in the day, 2 hours per, the same, 12. So that's why we got that 24 hours calculation. That number came because of the observation of zodiac constellations, which Babylonians did, of course. That's okay. I think we can now get back to enough of these constellations, get back to our subject of mathematics. Enough of astronomy. Probably I may get back to astronomy for a little bit when we are discussing Isaac Newton's theory of gravity, but otherwise we would do mathematics. No? So like I said, this period, Pythagoras probably went to Babylon, that is Iraq, or maybe Egypt. Part of Egypt, like I told you, was part of that civilization. So I went there and studied all their, whatever knowledge they had. He brought the whole thing here and started one Gurukula. There is a brotherhood there, Gurukulas. And all those people were there called Pythagoreans. They were Pythagoreans. They had to follow very strict rules. Every day they had to do work so much and study so much and eat so much or don't eat so much. All that they were doing, and they did good work there, I think. So when we name the theorem, Pythagoras theorem, we are respecting not just Pythagoras, because Pythagoras probably didn't discover a single geometry theorem or whatever. He didn't prove anything. But then he brought the knowledge. He's brought that knowledge where it was available freely. People were freely distributing it, and he simply has brought it. So we give respect to all those people, all those Babylonian mathematicians, by giving that name Pythagoras theorem. Then, as part of this, around the same time, we have our friend, 500 BC, Panini. Panini is an Indian scholar, was an Indian scholar, and India at that time had so many different cultures. Each culture was speaking some language. It sounds like Sanskrit. It's not Sanskrit. So they were actually called Prakrits. Prakrits, not one. There would be probably there are hundreds of Prakrits languages. Is more like a vernacular language. Like we have Bangalore Kannada, Mysore Kannada is slightly different. Davanagere Kannada is Mangalore Kannada 100% is different. You understand? So we have these Karwar Kannada maybe different, North Kannada, South Kannada. We are different. Just for one language, we have so many what are called vernaculars. No? They are actually called vernaculars, and the problem with vernaculars is that they keep changing. Every other day, new word is added by that group and it becomes part of that particular language. So when we want permanent documents to be produced, what we want is a pure language, purified language, which has very strict rules of formation of sentences and so on, very strict rules of grammar. So that is the intention of Panini. So he developed a treatise, what is known as Ashtadhyayi. Basically, that is Sanskrit grammar. Sanskrit grammar, which is excellent for recording purposes because it doesn't change. It's very strict in how the sentences are formed or how poems are formed, or extremely strict there. So obviously that doesn't change over thousands of years. And most of this Sanskrit old text was written in a poem form only, not the prose. Reason is very simple, because the way of communication is oral communication, and very easy to commit these poems to memory. So in fact, most of the Vedas and earlier texts have been passed on from generation to generation for the past 2,000, 3,000 years, orally only, no written document. So obviously, pronunciation also is a very important part of this, phonetic. So it is phonetic. At the same time, it becomes a record. You can call it a good recording language, more than a spoken language. Of course, Sanskrit was used in the courts as a court language. So we have three kinds of languages, really speaking. One is whether a language is good for recording. Recording means writing documents and passed on generation to generation for exchange of information. Then next we have the vernaculars. It's a spoken language, which is you can call it impure if you want, because they keep adding new words and new style of grammar. Then lastly we have court languages. In court is not our court. I'm talking about the king's court. In the court, obviously you can't use vernacular because you have to be very clear what you tell the king or what the king tells you. So they probably use this recording language for accuracy. Just like any document you give to the court cannot be simply some plain English like that. You have to whereas, whereat, where before, and here it, and all those words you add, and you see it's a complicated English. You understand that kind of language that you have to use in court, correct? So Sanskrit became a good recording language. Now, where does that leave us? Is the next question. I will answer that. Okay. Yeah, you can say about something about Sanskrit becoming a recording language because of the way Panini wrote the Sanskrit grammar. I'll just get back to that subject in a while, couple of minutes. You can imagine same thing should have happened elsewhere also. No, I mean this is a general problem because people when they speak vernacular language is not a pure language. No, so and we need a pure language to communicate to next generation and to others and so on. So Europe had the same problem. First, of course, Greek itself was the recording language, because they are the first scientists and first mathematicians. Greek was a language, so you will find quite a few symbols or names of Greek, like Helio, and many names of and many Greek letters, like alphabet, no? Like alpha, beta, gamma, delta, epsilon. All these have become part of our daily usage, because Greek was the original geometry people, mathematics people. But then Greek influence was only for a very short time, maybe about 500 years. If you look at the history, Romans took over that role, because Roman Empire was a huge empire, and obviously when Roman took over, the court language has to change. It can't be Greek. Romans don't want to speak Greek, and what do they want to speak? Italian, correct? But Italian has the same problem, has the same problem as our Prakrits. Italian spoken here and spoken in the next town are not identical. They have the same vernacular problem. So now we want to select one Italian, like we have to select one Kannada, for example. Would you select as a court language, would you select Bangalore Kannada or Mangalore Kannada or Mysore Kannada? Tell me. You understand the question? I would select Mangalore Kannada, because their language, the way they speak is almost like the way they write. So that's what you have to see. So they looked for a version of Italian which is a good recording language, and that name of that language, Italian language, is Latin. Latin became the ipso facto standard of so-called court language communication among scientists across generations for more than 1,500 years in Europe, elsewhere. So Latin is that important. I think there was a small village where the people were actually speaking Latin. Like today people say there is a small village where they actually speak Sanskrit. But frankly, if you ask me, that is really not true. It's not this Ashtadhyayi Sanskrit, at least. It is a vernacular, you can call it a Prakrit if you want. It's definitely not Sanskrit. But it doesn't matter, they are making a good attempt to bring a dead language alive. So Latin, I think in that way, today probably there is nobody who speaks the language. But then they found it is an excellent recording language. So that's why you find today modern terms in medical field and mathematics and physics and astronomy, almost every field that you take, you will always find Latin terms, or the names of tablets that you take will have a Latin name only. So Latin became that important. And in Europe, if you want to become a scientist or mathematician, what is the first thing that you learn? First subject is not maths, it is Latin. So you have to learn Latin first and then talk of anything else. So that's how it became. That is fine. As an official language, of course, the Sanskrit itself was the court language, communication language for thousands of years, as we understand. And till the development of science or mathematics went outside India, Sanskrit was still the language of recording and communication, correct? And this Ashtadhyayi also has been mentioned. It's not like any other grammar that you read, a book like a Wren and Martin Grammar of English or any other language. There are grammar books. It's not like a regular grammar book. It is written using meta symbols in a style of very advanced artificial language programs that people write today. So that means it has got a great significance, that style of writing the Sanskrit grammar, this particular Ashtadhyayi, is so fantastic. That is of interest even today. People want to use that style for development of the probably next generation of artificial intelligence programs or whatever. So that is the importance of that language. That's why I mentioned his name there. That's why we want to pay tribute to Panini because of that. That's a different issue. He was probably his grammar inspired many of these mathematicians in India and elsewhere. One aspect. Second aspect, it was necessary to learn his grammar because you have to write it in Sanskrit, obviously. So both ways, he was important. But then in Greece, we have a similar gentleman. We should pay tribute, Euclid. What Euclid did was, there are many things which we have got from Babylon, and there are many things these Pythagoreans have discovered regarding shapes, geometric shapes like triangles, squares, rectangles, circles, pentagons, heptagons, octagons, and so on. So let us formulate that as a treatise or a textbook so that it will be very easy for future geometers to study and make use of. That is Euclid's Elements. Euclid's Elements is a book which was originally written in Greek language, of course, obviously. But then very quickly it was translated to Latin, so you can imagine. And that was a prescribed book of mathematics for over 1500 years or something, even till Newton's time. So first subject to study was Latin, second subject is Euclid's Elements. You understand now? So that is the importance of how great those people were for us to remember their names. Euclid's Elements is a geometry fundamentals. What I will do is, as part of our sessions that we're going to have, I'll have a brief look at the basically what is there in Euclid's Elements. As part of our geometry discussions, that is fine, correct? Then we come to the next person who was a philosopher, primarily Aristotle. Aristotle, I have written the name here not because of philosophy, but because he presented a, what I might say, a coherent picture of the universe. All this time, till this time, people knew moon was going around in circles, Mars was going around in circle. They never thought it was an ellipse. Everybody thought it was a circle, right? Slightly elongated circle. But then a clearer picture of it, and Mars was having this retrograde motion and so on. So a scientific explanation for that retrograde motion, everything. He gave a coherent picture with a system where, of course, Earth is at the center, non-moving. Like I told you, Greeks never believed Earth revolved around its own axis. And these 7 planets are going around. See, that does not change. That picture does not change. And that is known as the geocentric system. Geocentric universe, you can call it geocentric universe. I told you, geo is the Greek word for Earth. So, Earth is at the center and the entire universe picture as part of this. Now, this geocentric view was perfected by Ptolemy after this. So, he also added, you can put both the names together. He properly explained this motion of Mars, some epicycles and some scientific explanation why it seems to go backwards and forwards again, all that. Very interesting part of it. And Al-Hasan al-Tusi in 1250, that means after nearly 1000 years later, he gave he made a device, what is known as a Tusi couple. It's actually a very simple mechanical device. If you can visualize one ring and on one more ring with exactly half the diameter inside. Now if you turn this one ring inside the other ring, you will find that this point, like I was telling about this Tusi couple is a very simple mechanical device which can explain. If you see a big ring and a smaller ring half the diameter inside, and if you move the small ring inside without slippage against the outer ring, you will actually find that the top point moves on a straight line up and down. Very strange. In fact, I didn't even believe it first, but then that is correct. So this can explain the retrograde movement of Mars. Thinking that Mars, if you think of that as a planet, is first of all going around in a circle of its own. A small movement on a circle which is known as an epicycle. and this circle itself is rotating or moving, revolving around the sun. And momentarily you can see it goes back, comes back, all that explanation becomes very simple. So I think Tusi gave a very good explanation of that movement. And Ptolemy also, I think, had some explanations, scientific explanations why Mars movement is like that. All other planets seem to behave fine except Mars for some reason. So Mars always has been the point of greatest interest to astronomers. You can see for thousands and thousands of years because of that. Okay. So this was the coherent picture which Aristotle gave, which for nearly 1500 years that picture did not change. Till our friend Copernicus, I have not even written his name here, I think, presented another theory which is not geocentric, but it is heliocentric. Helio is again a Greek word, means sun-centric. So it is again solar system. What we see as a solar system today, which is heliocentric system, where the sun is there at the center, all planets are going around the sun. That is the picture which Copernicus gave somewhere around 1540, 1550 or something like that, around the time Galileo invented the telescope. So Galileo could actually verify this heliocentric system of universe also. So that is the development in astronomy, which in turn developed into calculus that we will see at a later date. Now my interest is we go back to our geometry only and arithmetic, correct? So, now you have Aryabhatta as a key figure. He is probably known as the father of Indian mathematics. So Aryabhatta produced basically two major treatises. The original copies may not be there. Probably some Pandits at a later date, after a couple of 100 years, they reproduce that and it is available. There are two volumes. One is Aryabhatiya that I have listed here. I have written a different date, that is different. That date is different, Aryabhatiya. Other one was on arithmetic and algebra, arithmetic treatise. Now, in the first few 100 years of Christian era, this duration, lot of Indian mathematicians developed and perfected the decimal number, positional number system that we use today. So that means the decimal system is so important as part of arithmetic. Computations with decimal system or representation of numbers with decimal system is, positional number system is very simple. I can have any number of decimal digits, call it bm minus 1, etc., all the way till b0, and also a fractional part, we put a dot in the center and write d1, d2, d3. We can write any number of digits. That means each position has got a power of 10, positive powers of 10 to the left side and negative powers of 10 to the right side. No? So that decimal system was perfected. How to multiply two decimal numbers, how to divide one number from another, how to subtract, how to take square root of a decimal number. These are all important arithmetic operations that was described in that arithmetic treatise. And he also solved quadratic equations. Another important contribution of Aryabhatta. We know the answer to the quadratic equation, solution to that on our fingertips, a square plus bx plus c equal to 0. What are the roots of that equation? Minus b plus r minus square root b square minus 4ac by 2a. We have by hearted. No? We use this memorization technique for doing that. But then the actual solution was given by Aryabhatta. That's the first time anybody has done that, solving quadratic equations. So Aryabhatta did many more things also. He worked on trigonometry, and one of the important aspects of the Aryabhatiya, which is basically an astronomical treatise, was a table of he called it the Jivas, so I'll write that name only. Jiva. That is starting from 0, then 3.75. These are angles actually, degrees, all the way till 90 degrees. Totally 24 values for this Jiva. What is this Jiva? I'll explain shortly. He gave that. It's actually known as table of signs. Anyway, that was one part of it, this table of Jivas. Then solving quadratic equations. Calculating the value of pi, which is the ratio of circumference to diameter, all that he did that. Very nice stuff, which is all available nicely in Sanskrit poems, so anybody can get hold of that Sanskrit poem, and anybody knows Sanskrit can understand it. Yeah, but the problem with the Europeans was that they didn't know Sanskrit. They have no idea of Sanskrit. Now, let's see what happens. So obviously some kind of translation is required, correct? For both, even for the decimal system description, which is given in Sanskrit. No, everything is our court language is Sanskrit. So everything is in Sanskrit. So obviously it's not available to everybody in the world, so to speak. Now, coming to this Jiva business of Aryabhatiya, here the purpose, I think, was they were trying to construct this homakundas or whatever of a circular shape which has the same area as a rectangle or a triangle and so on. So they wanted to calculate some numbers on that, and for that aspect he did what is known as a parikramana. This is the movement of a person. I'll write that in Devanagari script. Parikramana is going around. No? We do in temples. Of course, temples we do clockwise. This parikramana, standard practice is to do it anti-clockwise. You just do one round. Supposing you walk one round, this will come handy in a triangle measurements, triangle for circle measurements and so on. So obviously this is of great interest in geometry. And if you carefully observe this person actually like a planet. We have the sun on one at the center. Imagine this is the sun and this is a planet. No? So planet actually wants to go straight in the tangential direction. That is the purpose, is moving in that direction. But unfortunately it is forced to go around a circle, right? So that means after some distance, or you can think of it as an angle. I'll just join this. We have moved some distance. We have moved some distance to the north. If you say this is the east direction, we have moved some distance to the north. I can measure by drawing a perpendicular. Correct? Now, what is that perpendicular? Which is part of that circle. Now you can see. In fact, if I extend that perpendicular to the other part of the circle, I get two intersecting points on the circle. No? So that such lines actually are called cards. That is a card actually. This is a card. But actually the distance which is travelled to the north is not card, is half card, half of that, exactly half of that card. And card is actually called a jya in Sanskrit. Jya is card. So this is ardha jya. So let me write that here. So this distance, which because of the circular movement, the amount of distance which has been travelled towards the north is ardha jya, and the distance it is actually traveled towards the center also. That is the horizontal distance, which is traveled to the center. Is also of interest, but actually more interesting than this distance towards the center is the balance distance to the center. So let me draw that line. That means actually two distances our friend is interested in, correct? So we got this Ardha Jya is one distance for, of course, a given angle. So you can think of this angle. And the other distance is balance distance to the center. And this distance is Ardha Jya. And to present that information in a Sanskrit poem, I think he didn't want to keep on saying Ardha Jya, Ardha Jya, Ardha Jya every time. Why do you want to keep saying that? Because there is no question of anything other than Ardha Jya. In the Jya, my only interest is always going to be Ardha Jya only in any case. So why don't we just call it Jya? No? So we just call it Jya. And he calls it Jiva. Actually, that's the name he gives. Jiva is actually half card. And the values of the Jiva for the different angles, starting from 0 till 90 degrees. Now, I did not even explain how that became 90 degrees. No? So, the angular measurement, again, from Babylonians to Greece, back to India. Remember, India, there was always a communication via Indus Valley civilization. No? So, some knowledge had been passing back and forth. There were traders, maritime trade was there. And this angle, the first thing was they wanted to find the diameter of a circle. Main purpose for that angle came because when you say, let me just show that as a separate sub-diagram, I'm going to rub this off. Starting from east, I start going around in a circle. If I go till west, direction west, what I have travelled is only half the circle, other half will be below, right? So now I want to give a name for this quantity, so that I want to call it some n degrees. Degree is the measurement, some n degree, so that I can measure any part of that as an angle. So now, what is the n value that I should use is the question Greeks had to answer, or probably even Babylonians, probably themselves, I think, answered that question. And for that they said, first thing is we need to measure this circumference, is half circumference, what is called semi-perimeter. So we want to measure this semi-perimeter. For that we need to actually go around a circle. So we start with a known distance from a point. A simple way of measurement is steps. In fact, many times I have seen land measurement, people do it with just steps. They don't have any measuring instrument because you can always make your steps exactly equal to 3 feet or whatever, approximately 3 feet, 3.5 feet, whatever. So if you put long steps, it may be 3.5 feet. But I have measured land many times, acres even, by exactly 3 feet steps, and I am accurate, 98% accurate in that measurement. So they said, so we'll start with this is the radius. We start with the radius of how many steps? How many steps we should have for this radius value, because we want to find the perimeter. So tell me how many steps. Obviously 60 steps, because 60 is a magic number. That is the number with any number that you ask for, you should say 60 only. Don't say anything else, right? So you are at a distance of 60 steps, probably holding a thread or something, so that you are actually walking on a circle. So something like our what do you call protractor? So something like this. So you start walking on it and reach the other side, which is the west, exactly opposite point. And they have walked something like 185 steps or something. Okay? It's not a round figure, little more than. I would have loved it if it were exactly 180 steps, because that would make it 3 times 360. So we'll do one thing. We'll call this 180 degrees. So that this, what we call right angle, becomes 90 degrees. And the complete angle becomes 360 degrees. So that is how that 360 degrees came. because of, again, original base of arithmetic of Babylonians. So, for angle 0 to 90 degrees, Aryabhatta gave the value of Jiva. That's the Jiva table. Very interesting information. Somebody wants to calculate for calculation for triangles, calculation for circles, all that is indicated there. No? So definitely it's very interesting, but unfortunately those people didn't know Sanskrit. So only who knows Sanskrit can understand. And luckily for the world, I don't know, luckily or unluckily, you can decide during this period, starting from, I don't know whether I can show it here or maybe rub part of it. I can show it this side. Somewhere around this point of time for the next 1500 or even more, 1500 years, there was a popular culture which spread all around the world, all around Asia, Africa, Europe. That is Islam. This Islam, Muslim rulers, they occupied most of the areas, and obviously, just like Greeks did to Babylonians, these fellows, when they come to a new place, they want to find out what is there freely available and take it away. So first thing some of the Muslim specialists did was to learn Sanskrit. They said, I have to learn Sanskrit, otherwise how do I read the great poems if they are there, right? So that's the question. So they learned Sanskrit, and somebody would translate that also to their language, and their language was Arabic. So that means you can see, if you take Aryabhatiya, which was written by Aryabhatta, was translated to Arabic in 820 CE. This is the translation time after 300 years. So this was translated to Arabic. From Sanskrit. Originally in Sanskrit, in 500 AD, 300 years later, it got translated to Arabic, and that is available in Arabic now. So, and obviously, if somebody in Europe wants to read about this treatise, Aryabhatiya treatise, which contains very interesting information about astronomy and triangles and all these details, you have to learn Arabic. Obviously, you have to learn Arabic. They had to learn Arabic, but then not many of those people could learn. So some of those Italian scholars, they learned Arabic. The purpose was to read this Aryabhatiya and translated that. So that means originally from Sanskrit it was translated to Arabic, and from there it was translated to Latin. And once it comes to Latin, court language of Europe, everybody in Europe will be able to read it. Anybody who's interested would have learned Latin language as their first language, and they'll be able to read this and then make use of it and have a great benefit, right? So now these translations also, there is always a language barrier, as you can understand, because no two languages can express the same thought equivalently. There is always going to be some change of thought or change of opinion or whatever. There is going to be, translations always create a problem, as we've seen. In this case, of course, it was a minor issue. When the person who translated, I don't know the name of the person who translated Aryabhatiya to Arabic, and he wanted to give this table of Jivas. What is this Jiva? There is no Jiva. He didn't understand the meaning of this Jiva, correct? Then he said there is a word in Arabic which is called Jib. Not even Jib, it is Jaib. I don't know whether I'm writing it correctly, but no. Not correct. How do you write Jaib?
Just correct, sir. One more big jar.
So he wrote it as Jaib. Jaib is the value. No? And in Arabic, normally they don't write vowels at all. Vowels are not written there. No? It is implied. So that means actually he wrote it as JB. If you might be to write in English, he wrote as JB. JB is the value of table of JBs, whatever that means. But the value is very interesting. So obviously, when these Italian translators read this document, they had to translate this JB. What is JB? There is no JB that they heard of, but there is a word in Arabic called Jaib is available. It is an Arabic word. They knew that because they had learnt Arabic. There is a word called Jaib, which is a fold in cloth, just a fold. So obviously they thought instead of using that as a fold in cloth, we will translate that as, that means Jiva became Jaib and that became Kov. Kov is two land masses which are jetting towards the sea, and the gap you see, that is known as a cove. They are all maritime people, right? Half of Greece is sea only. You can see that Greece, practically an island. Greece, Italy, all these places. England is like Ceylon, something like that. So it is a cove. So they want to translate that as cove. Cove I have written in English. Actually, you should write that in Latin. Obviously, they have to write that in Latin, and the Latin for that is sinus. And Aryabhatta had given a name for the vertical distance travelled as Jiva, right? And the horizontal distance also is interesting. So he had called it, I don't know why, Koti Jiva. Or Kote Jiva. So Jiva and Kote Jiva are the two numbers which are of interest. So obviously in Latin translations they became sinus and cosinus. That is the sine and cosine. You can see if you have the diagonal as one unit, these distances are actually sine and cosine. So you want to call, for example, now we need to pay our homage, tribute to Aryabhatta. We are giving tribute to Aryabhatta because we are named one satellite after him, and we have got some research institutes which are named after him. But after this knowledge, would you like to call him the father of trigonometry or something? Sin theta, cos theta. But unfortunately, no. People recognize Al Hasan Al Tusi. He was one of the greatest mathematicians, the greatest mathematician in the medieval Islam, the whole community. So he is recognized as father of trigonometry because he gave some good contributions in astronomy also. That is one result of Aryabhata's translation. Next, we have the other part, quadratic equations. That is also an interesting result that came out of that second part. So I think we should give proper respect to Aryabhatta. I think we should give more respect. So when the arithmetic treatise was translated, it was lapped up by these Muslim mathematicians because they found extremely interesting information in those. And one of those popular fellows, Al-Khwarizmi, in 840 Christian era. So he found that this solving quadratic equations, what has been proposed by Aryabhatta is fantastic. They have never seen the like of such arithmetic before. But there's only one problem. See, remember, this is presented as a series of poems, and the presentation is not good. When you say, I want to solve a quadratic equations, we need to write that in a step-by-step way, series of steps. Actually, we need to specify a series of steps. Supposing you say you got a quadratic equation and you want to solve, so I will tell you what to do. Step 1, you do this. Step 2, you do this, and so on. So I give n number of these steps. All somebody had to do was to follow these steps, and they solved the quadratic equation. So So he said, I will do that. And he produced a document in Arabic which gave a step-by-step method of solving. I mean, solving quadratic equations is one aspect of it, and a decimal arithmetic description, how to do decimal multiply, how to do square root and so on. So he gave all those, also other part of it. So it's a complete treatise, or 2-3 treatises that he wrote, all in Arabic, of course. And I don't know the full Arabian name of that Arabic treatise, what Khwarizmi wrote. I'll get a part of the name because that is what is interesting for me right now, is a compendium, that is the Arabic name for the treatise, compendium of, I'll write that in Devanagari script, Algebra or Mukabala. Mukabala is balancing. Balancing arithmetic statement is transporting left to right, right to left, and we know transport from one side to another side. No, it is called Mukabala. Right? And what is algebra? Is completion of square. So this is completion and balancing. So the method was one of these steps to actually complete the square, one square, and other step is to do the balancing, and finally once you follow all these steps, you got your answer, no? You got your roots of the quadratic equation. So it is a really fantastic text that Khwarizmi wrote. So we'll see what happens to this Arabic text of Al-Khwarizmi. You have to see that now something happened to our earlier text of sine table, no? Jia table. Same thing is going to happen here also. I'd like to tell that next.